Why is the research that DeepSeek did with their R1 model so important? Well, basically, it paves the path to artificial general intelligence and possibly artificial superintelligence, and it could be here much faster than we expect, and it's all due to reinforcement learning. So let's take a look. Hey y'all, it's Dr. Know-It-All. I'm super excited to talk about this DeepSeek R1 incentivizing reasoning capability in LLMs via reinforcement learning paper from DeepSeek AI. I don't see authors listed in this, unfortunately. I have a feeling it's some of the folks that reference themselves throughout this. Anyway, I have got some coffee. I have got a nasty migraine headache, which I fortunately don't get headache symptoms, but I can't see. I have lightning all over my eyes. It's the craziest thing. Anyway, when I first got it, I thought I had a brain tumor or something. Fortunately, the doctors just told me it was migraines without headache symptoms. So anyway, I can't really see what I'm looking at right now. So I think it came from reading this paper on a very, very sunny day. I think that tends to be sunny, dry, tends to cause these migraine things. So anyway, if you have those kinds of symptoms, ask your doctor about whether you get migraines or stuff. But regardless of that, this is a really, really important paper. This is a huge milestone. And by the way, very well written paper. Thanks, guys. The Titans of AI, that paper was pretty bad. It was poorly written. I told people I'll call you out if you do it wrong. I'll call you out if you do it well. This is a very well written paper. Extremely good. It goes into just the correct amount of details so that you know exactly what you need to know. And yeah, so congratulations to the folks at DeepSeek for doing this. They did a fantastic job. Anyway, before we even start, let us talk about reinforcement learning. This is something that we have heard about for a long, long time, right? I mean, we're talking about back in the chess playing era, when people were developing things to play chess better. Now Deep Blue was not this, because that was just brute force, basically. They were like, how many different, paths can we look through? Sort of Monte Carlo search. I mean, I think it was much more sophisticated than that. But anyway, it was essentially just sort of brute forcing their way through chess. But when you get to a game like Go or something, you can't do that. There's just too many options, more than atoms in the universe, that kind of a thing by orders of magnitude. So there's two options instead. Number one is you can train an algorithm based on the best human players and give them supervised training data. In other words, human games and stuff for the case of Go. And that works, and it actually beat Lee Sedol. That's what DeepMind actually did back in 2015, if I'm remembering correctly. But then they developed AlphaZero to that name. So notice that we have down here DeepSeek R10. That is very, very specifically related to DeepMind. It's a callback to them. But basically what they said was, here's the rules to Go, and here's player A and player B, white chip and black chip, white stone, black stone, etc. And you guys play millions, hundreds of millions of matches versus each other. We don't really give you much of a reward system. We just, whoever wins and loses, that's the reward for the game. And of course, at the beginning, they were absolutely terrible, but they learned really, really rapidly, and they actually outstripped human performance very, very quickly. And now, of course, the best Go players in the world are learning from these things how to do moves that no human being had ever thought of. I think it was the famous move 37 in the Lee Sedol games matches. That was a long time ago. Can't remember exactly. Gosh, that was a decade ago now. But anyway, that was with the human trained version of this. With AlphaZero, it was on its own. It just learned how to play. So the advantage of reinforcement learning is that these systems, once you set it up properly, can play each other ad infinitum. They can just keep going and going and going. They're not limited by the amount of data that is available from humans. And if you've been paying attention to the internet, people keep talking about how we've used up all the data on the internet and everything, right? On the internet, talking about that. But that basically all of human data has been absorbed already into these large language models. What are we going to do? Well, this is the answer. Just let them play themselves. So of course, I and many others have talked about reinforcement learning for large language models for years. It's the obvious next step. It removes the bottleneck of humans, and you don't have to have the human data, and you also don't have to have humans supervising this training. It can just do it on its own. What is the disadvantage? It's the sparse reward system. Let's say you want your model to solve a very, very complex math problem, coding problem, whatever, something that requires a lot of thinking. Well, there are many, 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 many steps between here's the problem and here's the solution. And the traditional way of dealing with this has been to kind of split it up into smaller steps and grade each step, like how well are you doing here? How well are you doing here? How well are you doing here? That gets a lot of human bias in there. You're getting your hands in the process a lot and telling it how to think. But rather than do that, what if you just tell it, this is the answer that I'm looking for, and let it go for it on its own? Well, the obvious problem with that is, let's just arbitrarily say there's 45 steps between, specifying the question and getting an answer. That means it has to get 45 steps right without failing in order to get to the answer. That is a very sparse reward system. At the beginning, you're going to have a billion wrong answers to one right answer. And the right answer is just by accident or something, right? So the reward is incredibly, incredibly sparse. But there's a bit of a cheat that they don't really talk about in this paper. But what they've done is they have a V3 model that they have created before, which is already a very, very smart model. My understanding is that they take the V3 model as their base model and use that to begin the reinforcement learning process. So they're cheating. They're giving themselves a smart model already. So what you're doing is taking like a high school trained student and putting them in college and telling them to do something, right? That's reasonable. You can't take a 2-year-old infant and put them in college and expect them to get any kind of benefit out of that because the reward system is just too abstract and too sparse for what a 2-year-old is able to handle. If someone with more knowledge wants to let me know, especially if you're from DeepSeek, please do let me know in the comments, and also hit me up on X. I would love to have a chat with you. In fact, I'll do it on this channel if you guys want to talk about it, because this is amazing. Also, by the way, this is open source. So not open data. They don't have all of the data that they trained on, but all of the weights and everything is open source. So huge congratulations. I mean, this is just an amazing, amazing accomplishment, and also amazing that they're sharing it with us. So anyway, I just wanted to kind of preface this because I wanted you to understand why this is so important. If you can figure out how to deal with this ultra sparse reward system in terms of reason to thinking, then you can turn it loose. Once you break that bottleneck and you don't need human data anymore, you don't need that supervised fine tuning or reinforcement learning through human feedback, stuff like that. Once you can get rid of that, or at least for the most part get rid of that, we'll see. There's 2 versions of R1 here, and it's very important. 0 is kind of a pure research project, and R1 without the 0 after it is more of a productized version, something that is more friendly to humans, but it involves many, many more steps than R10 does. And by the way, a little insert here, my 60th birthday is in just a few days, so if you don't mind subscribing, that would be a fantastic birthday present. Thank you so much in advance. One of the things they do with R1 that I think is actually kind of a shame is that they remove something that R10 did, and that is it's trained on Chinese and English texts primarily for reasoning. And what it started doing was mixing languages in its reasoning process. And they actually got rid of that because they said it was confusing to read and to understand. And I can understand that, but I think that's probably a feature, not a bug. So we'll talk more about that in just a few minutes. I think that's also a fascinating element of this. Anyway, as you can tell, I'm pretty pumped about this. It's not just the coffee. I'm really pumped about this paper. I think that this is a real unlock. If you combine this with some good memory or something like that, some of the stuff that we saw in the Titans paper. If you haven't caught those, by the way, definitely check out my testing of R1, which I already did, and the Titans paper. I'll leave links to those up at the top and also at the end of this, because I think it's well worth, looking at all of these together. This is a big deal. All right. Anyway, they're abstract. We introduce our first generation reasoning models, DeepSeek R1 and DeepSeek R1. Like I said, 0 is more of a pure research project. R1 is more like a product that you might want to produce. DeepSeek R1, a model trained via large scale reinforcement learning. Large scale, I don't know how many epochs they did or how many steps, but it must have been a lot because they say large scale over and over and over again. Without supervised fine tuning, or SFT, you'll see that a lot in the paper, SFT, so just remember that. As a preliminary step, so just straight up large scale reinforcement learning without any preliminary like cold starts or anything like that, demonstrates remarkable reasoning capabilities. Through RL, or reinforcement learning, DeepSeek R10 naturally emerges with numerous powerful and intriguing reasoning behaviors. They don't tell it to reason. They don't tell it how much to think. It figures all of that kind of stuff out. However, it encounters challenges such as poor readability and language mixing. And I think I said here, this is a feature, not a bug, right? Yeah, this is a feature, not a bug. It's the beginnings of an internal new reasoning language that could be AI specific. So cool. So what I'm thinking is we're going to have something where AI is going to start thinking in its own language. It's going to have its own reasoning language. It won't use English. It won't use Chinese. It won't even probably ultimately use a mixture of the two. It'll have some sort of internal language that it develops on its own. If you allow it to do this reinforcement learning without constraining it at all, it will develop its own language, which will probably at first look like a normal human language, but but will drift away from that over time and become probably way more efficient and allow it to think about things in a way that's much more efficient and aligned with what these neural networks actually naturally want to do. So that's just cool stuff too. So stay tuned on that one. That's a for future reference, but I'm planting a flag in the ground that I think these models will eventually reason in languages, whatever you want to call that are different from human languages. And we eventually won't even understand them. We won't know what the hell they're thinking because we won't be able to read it anymore. Anyway, continuing here, to address these issues found in R1.0 and further enhance reasoning performance, we introduce DeepSeek R1, which incorporates multi-stage training and cold start data before reinforcement learning. We'll talk about that later. DeepSeek R1 achieves performance compatible to OpenAI 01/12/17, which is the date they released it, on reasoning tasks. To support the research community, we open source DeepSeek R1.0, DeepSeek R1, and 6 dense models at 1.5 billion to 70 billion, distilled from DeepSeek R1 based on Qwen and Llama. And that is also a huge deal. I'm going to go up here and show you this graph while we're talking about this distillation, but distillation is also incredibly important. What they learned was to run reinforcement learning on these small models, 1.5 billion, 70 billion, whatever. These are smallish models. To run reinforcement learning directly on them just didn't work, but they were able to distill, the teacher model was able to distill the information down to these tiny, tiny models, and they actually totally crush their own models, the very same model that hasn't been retrained basically using R1. And that is a pretty incredible metric as well. It means that not only do we get these massive frontier models that are huge, difficult to run unless you have, a huge number of H100s or something like that, you can also distill incredibly smart models, especially if you want to go for specific, domains, if you want to go for programming, or if you want to go for math, or if you want to go for customer service, whatever, think about it that way. You can train these things up, these very, very small models, to be really, really intelligent in a specific domain. And that is also a huge result of this paper. And one of the reasons why open sourcing this stuff is so important, because open sourcing means that people will be able to do this and quickly. Anyway, so the striped bars here are DeepSeek R1, not R1.0, but the sort of reinforcement trained one. So we'll get into the details. So you can see that it's basically doing the same as OpenAI's 01, right? That's the gray bar next to it. It's either just underperforming or just outperforming it. You can also see in their light blue, which is the far right one, that their V3 model is substantially worse, and that's not that old at this point. And also that their R132B, which is a Qwen model that was distilled from this, which is this kind of darker blue color, also does an amazingly good job. Now, obviously not as good as these frontier models, but on things like Math 500, 94.3 is just outstanding and actually really outperforms OpenAI's 01 Mini as well. So that does very, very well as well. The SWE benchmark, not so good, but the other ones it actually does exceptionally well, especially considering it's only a 32 billion parameter model. All right, so now let's get into the meat of this paper. I am not going to go through the performance testing benchmarks, all of that kind of stuff. I will, of course, leave a link to this in the description so you can check it out yourself. It's just a DeepSeek, by the way. But anyway, I don't care about that in detail. Obviously, this thing does really, really well. It's more like, how does it work? That's the important part for this video. I think you guys want to know. It's a deep dive here, so we want to know. So anyway, they talk about how LLMs have diminished the gap towards artificial intelligence. Notice that's they're thinking about that. And that we can see that post-training has emerged as an important component of the full training pipeline. And of course, that involves inference time scaling, in other words, the amount of tokens you're allowed to do, and increasing the length of chain of thought reasoning processes, so giving it more time to think at inference time. They also talk about 3 methodologies that have been used before, which is process-based reward models, which they reject, Monte Carlo tree search, which they also reject. They tried both of those, and reinforcement learning, which is obviously the winner here. So as they say here, in this paper, we take the first step toward improving language model reasoning capabilities using pure reinforcement learning, or RL. Our goal, so they're not doing anything else. That's what the R1.0 is. It's just reinforcement learning, nothing else. Our goal is to explore the potential of LLMs to develop reasoning capabilities without any supervised data, focusing on their self-evolution through a pure reinforcement learning process. We use DeepSeek V3 base as the base model, so there we go, and use GRPO as the reinforcement learning framework to improve model performance in reasoning. So yeah, so they start by cheating. They use a model that's already smart, right? Like I said, you take a high school student and put them in college. You don't take a 2-year-old and put them in college. So that's really good. And as I said over here in my little comment, I said, F the other stuff, just let it play. And that's the goal of this, right? Just like with AlphaGo, it's just like, let this thing go. You've got a reasonably smart model, give it a reward system and give it a lot of questions and let it just crank on that and see if it gets smarter. And just to mention benchmarks here, because I'm going to skip that section later on. After thousands of reinforcement learning steps, DeepSeek R1 exhibits super performance on reasoning benchmarks. For example, pass one score on AMY 2024, in other words, get it right the first time, increases from pretty dismal 15.6% at the beginning to 71%, and with majority voting, so in other words, you take a bunch of possible answers and vote on which one's the best, the score improves to 86.7%, matching the performance of OpenAI's O1. And as I said earlier, the problem with DeepSeek R1 is you get mixed language, you get complexity in terms of understanding what it's thinking, all of that kind of stuff. That is a problem. So they trained a different model using a pipeline, DeepSeek R1, which is much more human friendly. But as I said in my comment over here, this is a new reasoning language. Soon it'll be too compressed for us to understand. It'll be that kind of a thing. It'll be like, we don't understand what it is, but it'll be efficiently processing stuff. Very, very scary, but also very cool that we could have this silicon that's inventing its own language and understanding the world in its own way without regard to, taking humanity as the basis, taking our language as the basis, but evolving that to the next level, whatever that is. So how do they create DeepSeek R1? Well, they incorporate a small amount of cold start data. In other words, just before you start the reinforcement learning, you give it a bunch of data and you say, hey, train on this. So how they collect that and all that stuff is intense. But anyway, they take high quality data, and I think it's about 800,000 samples, and they give it those samples and they let it crank on that for a while and begin to fine tune itself before it moves over to the reinforcement learning step. Anyway, then they use a multi-stage training pipeline. Specifically, they collect thousands of cold start data to fine-tune the DeepSeek V3 base model. Following this, we perform reasoning-oriented reinforcement learning like DeepSeek R1, same basic process. And then, upon nearing convergence in the RL process, in other words, it's getting close to as good as it's going to get, they create new supervised fine-tuning data through rejection sampling on the reinforcement learning checkpoint. In other words, they sample a bunch of stuff, reject the stuff they don't like, keep the stuff they do like, and then finally you combine that with supervised data from DeepSeek V3 in domains such as writing, factual Q&A, and self-cognition. So things that don't have an obvious correct answer. Much, much easier. I've talked about this before. It's much easier to train math and even something like the ARC challenge with the little, squares and stuff like that where you have to answer these questions. Much, much easier to train on something like that because it has one right answer. Super much more difficult to train on something like creative writing or something because what's the right answer? It's like it could be anything. It's whatever the creative person wants. So anyway, they do throw some of this stuff in, but these models are not necessarily going to be fantastic writers or anything. They're much more reasoning engines. They're much more about that kind of stuff. But anyway, so they do actually, pay some adherence to that and throw some of that data in at the end in this last sort of fine-tuning step to allow it to think beyond just the bounds of yes, no questions or, there's a right answer, there's a wrong answer type of questions. Anyway, so then they retrain the DeepSeek V3 base model. It's a little bit unclear whether what they're talking about here is that they take DeepSeek V3 base and retrain it entirely. I don't think that makes sense, but I think what they do is they take the model that's evolved from DeepSeek V3. I could be wrong about this again, but my understanding is that they would take this model that's basically almost converged and then fine tune it with this new information. And then the next sentence here, after fine-tuning with the new data, so maybe they're fine-tuning V3 base model and they're going to use both of them together, something like that. I don't know. Again, it's a little bit unclear here. The checkpoint, so that would be this R1 model that's improving and improving, undergoes an additional reinforcement learning process, so it plays itself, taking into account prompts from all scenarios. So it's looking at all of these different collected pieces and it's training on that as a fine-tuning, final fine-tuning, icing on the cake sort of thing. And then, of course, they talk about distillation from this teacher model, this R1, this very, very large frontier model, down to these smaller models, Quen and Llama. And I have heard rumors on X that Llama 4 may have been tossed out the window, that Meta may have looked at this paper, looked at R1 and gone, holy crap, Llama 4 sucks. It's not going to be, worth even releasing. And we're going to do a new version of Llama 4 based on this stuff. Totally just a rumor. Again, if anybody has more knowledge, I would love to know about that. But really fascinating if Meta threw away what would be, millions and millions of dollars worth of training and everything on their new Llama model, which I'm sure they were probably getting fairly close to releasing. If that's the case and they just thought, nope, this thing sucks compared to what's going on here, then you can expect over the next few months that they will retrain a Llama 4. So if Llama 4 comes out next week, you can pretty much guarantee they didn't take account of this paper. But if we start hearing about delays to Llama 4 and maybe it doesn't come out till May or June or something like that of 2025, then maybe what happened was they actually took account of this paper and they said, oh, holy crap, what we were doing is absolutely not good enough. We need to utilize what they're doing in this model. And again, this is one of the reasons why open sourcing this thing is such a huge deal. And going into such detail in this paper, OpenAI has taken to just doing press releases where they don't talk about what the hell they do. This gets into a lot more detail, so you could actually replicate this yourself if you had, the resources to do that. I certainly don't. But it's very, very exciting to see this stuff and to see how this might disrupt the industry. So their contributions here are large-scale reinforcement learning on the base model. So in other words, they're able to take this base model, reinforcement learn on it, that the high school student, teach it to be in college, then graduate school, then, whatever. So teach it to be much, much smarter based on just playing itself. And they do it without relying on supervised fine-tuning or SFT as a preliminary step. And one of the big things is it basically learns to think. It wasn't taught to reason or do these large chains of thought. It figured it out on itself, which we're going to get to in just a minute. So you can see it evolves and literally evolves capabilities. This is emergent stuff. It was not programmed in. Self-verification, reflection, generating long chains of thought, marking a significant milestone for the research community. I totally agree. It's the first open research to validate that reasoning capabilities of large language models can be incentivized purely through reinforcement learning without the need for supervised fine-tuning. So that's what R10 was. It was just a pure play. Can we do this? Yes, we can do this. And it actually works pretty darn well. And then they talk about the development of R1, not 0, in terms of getting it closer to what humans like, aligning it with human preferences, and making it work through a pipeline of refinement stages. And of course, then again, they talk about distillation, which is also a very big deal. So then they get to their approach. They say, previous work has relied on large amounts of supervised data. In other words, labeled and all of this stuff, a lot of human hands in the mix. It's very, very slow process, very cumbersome, all of that. So it reduces the ability to scale. In this study, however, they demonstrate that reasoning capabilities can be significantly improved through large-scale RL, even without using supervised fine-tuning as a cold start, which is what they do in R1. So this, again, it's just a pure play. Can we do this only using reinforcement learning? Again, with a smart base model, but so you can't just do it from scratch with completely randomized weights. But if you have a good base model, you can train something up really, really well without the need to have human intervention. But then, of course, they say that performance can be further enhanced with the inclusion of a small amount of cold start data, in other words, for R1. And then they're going to present DeepSeek R1 which is the reinforcement only version, DeepSeek R1, which applies reinforcement learning, starting from a checkpoint fine-tuned with thousands of long chain of thought examples. So they cheat, they give it a head start. And then 3, finally, the distillation of reasoning capability from DeepSeek R1 to small dense models. Then down below, they show us a very, very hairy equation there. Kind of broken it apart and looked at it a little bit myself, and I'm like, ooh, okay. I'd have to think on that one for a while to really understand it. There's pieces of it, and there's mins, max, and how the whole thing works. But anyway, so they basically say they explore the potential of large language models to develop reasoning capabilities without any supervised data, focusing on their self-evolution through a pure reinforcement learning process. And by supervised data, they don't mean no data at all. They mean they're basically just giving it the question and the answer. They're not giving it any of the steps. They're not supervising it. They're not labeling it. All of that kind of stuff is missing. And then I think one of the authors is Shao here because he mentions himself. So anyway, in order to save the training costs of reinforcement learning, we adopt group relative policy optimization, or GRPO, which I'm still trying to wrap my head around, to be honest. But basically it forgoes the critic model because the critic model can be as large as the generative model. So if you imagine this frontier model is 1 trillion parameters, you have to have something that's just as smart as that to criticize it, which means you need another model that's 1 trillion parameters. And you have to run both of these things things in parallel. This was something I did a lot of when I was in grad school. I did generative adversarial networks. In other words, what you would do is take two networks, and they were at the time convolutional neural networks, but so whatever. Seems super primitive nowadays, but 8 years ago, 9 years ago, it was actually, it was pretty reasonable at the forefront. But anyway, you have to train both of these things in tandem with each other. The critic model has to get smarter and smarter, and also the generative, the creator model has to. And if one of them gets significantly smarter, it can game the other one. It's not particularly easy to keep them in balance, and it also, doubles the amount of time. And this is a Chinese company, and, the political facts are what they are. NVIDIA and others are not allowed to give them their latest chips, so they are resource constrained, so they've had to become more creative. I think it was Dave Shapiro recently said that, ironically, by restricting the amount of stuff that Chinese researchers have access to, you're kind of forcing them into a creative Cambrian explosion. So they actually may produce better stuff because of the fact that they don't have these massive resources. They can't spend $50 billion on some sort of data center in order to train these things at that sort of level. If they've only got a couple $100 million or something, or even a couple of $1 million, they have to be much more creative about how they're going to train it. So this may be one of those outcomes. So anyway, GRPO estimates the baseline from group scores instead. So I think what it does is it kind of generates a plethora of answers, and then it kind of goes like, okay, I think this is the baseline. And then what it does is this A down here, this A sub I, is actually what's called the advantage. And that advantage is like how far kind of above the crowd is this. So I think I'm understanding this correctly. You're taking, a population of answers. So let's say there's 100 answers. I have no idea, arbitrary. But let's say there's 100 answers, and you look at, there's like an average of all these things, right? And you look, some are worse, some are better, and some are really, really better. And you look at those and you go like, ooh, that's a substantially better answer than the average answer. And so that's an outstanding thing. So let's go that direction and look. And then of course they have to add some factors in like minimization and stuff like that, so you don't take too big of a step. A little bit like gradient descent in the sense that you look for the best path downward. What is the most severe slope going downward in the energy path? You want to follow that one, but you don't want to take gigantic strides down there because you might go way too far. So you want to do that, and then you want to cut it back. And that's the learning rate you might hear about in deep neural networks. You actually take that, and let's say it's a 10th or something. So you want to take a step of 10. Well, you multiply that by a 10th, and you only take a step of 1. So you take a little baby step in that direction rather than a huge one. So here you're looking for what's outstanding above the group, but you're taking a little step towards it. You're not going all the way because you may overshoot that answer. It might be outstanding from the group, and it might look like it's better, but it might be reasoned really poorly. So you don't want to go too far that direction. You just want to go a little ways and then look at the next question and see what those things are, right? So by doing that, by taking little steps, you don't get there as fast, but you don't also completely overshoot and go off into who knows where. Then they talk about formatting. So this is really interesting. And this is the kind of thing you might have seen with GPT-01 if you've used that and stuff. Of course, you can't see the actual thinking, but they put think tags. So they have basically just a markup language here. So they have think and then unthink, right? And in between that is what it thinks. And then they have answer, unanswer. And within the answer tag is actually the answer. So generates a bunch of thoughts. Yeah, what am I going to do? All this stuff. And then finally it gets an answer, which might be as simple as a single token. Like maybe it's a multiple choice question and it's like A, B, C, D, and it's like D. Right? So it could produce one token for the answer. It could be as small as that. But in the thinking, it could take a very long time thinking about that. So it's really cool how they're looking at this and how they're forcing it to fit within a certain kind of framework so that it's easier for us to understand and for it to differentiate the thought process from the answer process. And that actually matters too, because eventually when they want to get it to be more human aligned, they actually talk about how they grade the answer, but they don't grade the process. They don't want to remove the ability of the model to think any way it wants to. They just want to look at the answer and see if that aligns with human expectations. So very, very cool that they can very easily through markup language determine what's the thinking part according to this thing and what's the answer part. So in terms of the reward modeling, this is how you reward this thing. Remember, this is sparse. It's only kind of at the end of it that you get this. You have two sort of rewards. They give it accuracy rewards for how accurate it is. In other words, in the case of something like math problems with deterministic results, which is why this is so much easier to do with this, the model is graded on the accuracy of the response, whether it's correct or not. That's very, very easy to do with this deterministic kind of thing. It also has to format it within a box so that it's, I guess the grader, which is not going to be be a human. It's going to be some other AI or something like that. Or not AI, it could just be basic code, but it can go through it. It could go like, oh, here's the answer. That's what I'm looking for. Ignore all these other thousands of tokens. Just look at this part. Is it right or wrong? And it can verify it quickly. But then it's also given format rewards. In addition to the accuracy, we employ a format reward that enforces the model to put its thinking between think and unthink tags. So that's also important as well. I don't know how they grade them, and I would expect it could probably learn the formatting rewards relatively quickly, so it may not be all that important, but you can't have it mixing up thinking and answering. So it's actually good that they do this, and I'm sure that they learned the hard way. They probably didn't do it at first, and then they were like, oh my gosh, it's just a mess. And here again, they specify we do not apply the outcomes or process neural reward model in developing DeepSeek R1 or R1 for that matter. They don't look at the process. They just grade whether it got it right or wrong. Very, very, again, this is the secret. This is the thing. It seemed like it was not possible to do something like this. They figured out a way to do this. The model obviously has to be big enough that you can start that way. Again, you can't take a toddler and teach it college stuff. You have to give it something, that you have to give it some education. So it has to be a reasonably smart model to start with. But at that point, you can just go with incredibly sparse reward systems. Just tell it whether it's right or wrong at the end of generating 10,000 tokens or something. Is it right or is it wrong? That's enough of a reward for it to eventually figure this stuff out on its own. That removes humans as the bottleneck. We don't have to sit there and grade it. We don't have to come up with the data. We don't have to label the data. We don't have to tell it throughout the whole process whether it's right or wrong at each individual step of the data, which is that process reward modeling. All of that stuff is thrown out the window. This really blows the doors down. It's like a dam breaking, and this is AI moving forward really quickly. They then talk about how they intentionally limit their constraints on the thinking process to this structural format. In other words, think part, answer part, that kind of thing. And they avoid any content-specific biases, such as mandated reflective reasoning. They don't tell it has to think. They don't say, give me a long chain of thought, that kind of thing, or promoting particular problem-solving strategies to ensure we can accurately observe the model's natural progression towards the reinforcement learning process. In other words, how it actually moves. So then they show us with a graph how it actually steadily improves just using reinforcement learning. So let's take a look at this graph down here. So you can see here that we've got the R10 pass 1, which is basically it has one chance at it. That's the blue dotted line. And then this one, I believe, is you're allowed to take 16 and you take the best answer out of 16. So anyway, so you can see how we've got an O1 pass 1 and an O1 generating 64 answers and picking the best one. So that's the green line, and the purple line, that's just a baseline, right? That doesn't change because that's what's already given. But you can see that at the beginning of the steps of training, they're both like really poor. Even the one that has 16 versions of it is at like 25% maybe. So, it's like a model that, again, it's a high school student. It knows a little bit of math, but if you suddenly throw complex math at it or something like that, it's going to be like, what the hell? So anyway, but you allow it to play itself, And after a while, we get above 70%, like 71% on single shot answers, and we get almost 87% if it has 16 chances at it and picks the best one. And it looks like it actually did well, and then it went back down again. This is the kind of thing that happens with training. Sometimes you just get a really good checkpoint, and so they might have actually wanted to go back to this checkpoint at like 6,200. It looks like they finally got back up there at over 8,000, but they had one very, very good sort of run at this thing. But anyway, the impressive part here is that it went from here to here without any human supervision. It just learned, and that's really, really impressive. And as they say down here, this is a noteworthy achievement that it's able to do this without human intervention. And as I said in my note over here, crazy how well this works. What will the next generation do? It might be here in weeks, if not months, since it's not human bottlenecked anymore, which is really true. And also could explain how OpenAI is releasing their O3 model very, very soon, only months after O1 rather than years. And as we're going to see in just a minute, there's actually indications with R1 that it could continue to improve without even having to go to a next generation. But anyway, we'll get there in just a second. It's the next page. So anyway, we've got self-evolution. The self-evolution process demonstrates how reinforcement learning can drive a model to improve its reasoning capabilities autonomously, in other words, without human intervention, by initiating reinforcement learning directly from the base model. So they don't give it any cold start data. They just like, go, here we go. We can closely monitor the model's progression without the influence of the supervised fine-tuning stage. And this is where they get to this graph. And this graph is really cool. So you've got an average in dark blue and then the kind of standard deviation or all of the different answers in the light blue color. But basically starting at, way down here, it doesn't think over on the bottom left, you can see that it's generating very, very few tokens. So that's the length per response. That's the number of tokens it's generating. And over time, as it learns and learns and learns, very progressively, it's not like a big jump all of a sudden. It just keeps going and going. It learns more and more to think harder and harder and generate more and more tokens. So by the end, you've got, average of almost 10,000 tokens generated per question. Some of the questions, like if you ask it an easy question, it doesn't require as much thinking. And so it will actually drop down the amount that it requires. And if you ask it a really complicated question, it might go up to 12,000 tokens or something. So it's also good that it's kind of learning how much effort to put in, right? If you just ask it a simple question, like, I don't know, recite the beginning of the Gettysburg Address, right? 7 years ago today, it doesn't have to think that much. It probably just has that on hand. So why would you want to generate 10,000 tokens thinking about, maybe it's got to do the Gettysburg Address, but maybe he meant this, right? That would be way too much. That's overthinking the thing. That's kind of level 1 thinking to recite something from memory. Level 2 thinking is when it has to think hard. And as I said in my note here, there is not a clear asymptote to this. In other words, it doesn't do this. It doesn't start to level off in terms of token generation. So what happens if you just keep training it? Will it get to 20,000 tokens generated per question? Will that make it a better model? Will it actually answer better? These are interesting questions for future research. Now, obviously, they got to a certain point. They were like, okay, we're done. Maybe it started to tail off in terms of its ability to learn. And that we could look at maybe this graph up here that, it's kind of becoming asymptotic at this point. It's like it is leveling off to some extent. So maybe they decided that generating more tokens wasn't particularly worth it. But it is interesting to think like how many tokens would it generate eventually? Because again, it doesn't seem to be slowing down. So what if they doubled this to 16,000 steps in their training thing? Would it be generating 20,000 tokens per answer as opposed to 10? Good question. So very importantly, as they say here, this is not the result of external adjustments, right? They didn't put their fingers in this and do this, but an intrinsic development within the model. It naturally acquires the ability to solve increasingly complex reasoning tasks by leveraging extended test time computation. It figured this out on its own. This computation ranges from generating hundreds to thousands of reasoning tokens, allowing the model to explore and refine its thought process in greater depth. And as I say in my note down here, the fact that it basically evolves, quote, evolves these features is a huge win for AGI and ASI. It means we can sparsely reward a model, and with enough play, it will figure out by itself the best way to get there. That is a pretty huge result. It's shockingly huge result. And as they say down here, these behaviors are not explicitly programmed, but instead emerge as a result of the model's interaction with the reinforcement learning environment. That's the real key to this paper. Then we get to the part that everyone's been headlining their YouTube videos and articles and everything, the aha moment, or eureka moment, if you want to go Greek. Anyway, a particularly intriguing phenomenon observed during the training of DeepSeek R1 is the occurrence of an, quote, aha moment. This moment, as illustrated in Table 3, occurs in an intermediate version of the model. During this phase, R1 learns to allocate more thinking time to a problem by reevaluating its initial approach. So it's thinking, it thinks it's almost done, and then it's like, wait, I need more time to think about this. That's the aha moment. This behavior is not only a testament to the model's growing reasoning abilities, but also a captivating example of how reinforcement learning can lead to unexpected and sophisticated outcomes. I like the way that they talk about this. They're really enthusiastic. They're like, this is cool. You can feel under this paper, they're being professional, but under this paper, they're like, we're excited. This is pretty cool stuff. And they say that right below. This moment is not only an aha moment for the model, but also for the researchers observing its behavior. They were probably like, popping champagne corks or something like that, going like, holy crap, it actually worked. Anyway, it underscores the power and beauty of reinforcement learning rather than explicitly teaching the model on how to solve a problem. Again, that's heuristics that as limited in terms of the possibilities. The world is just too big of a world, too many edge cases for you to do everything. You can't program everything in. So rather than teach it how to solve the problem, just provide it with the right incentives and it autonomously develops advanced problem solving strategies. So what is it doing here? It's trying to solve this equation of root a minus root a plus x equals x, square both sides, doing this stuff. And then this is the important part right here. It says, wait, that's an aha moment I can flag here. Let's reevaluate this step by step to identify if the correct sum can be blah, blah, blah. And then it goes back and starts working on this again. So it's that nature of saying like, wait, or I think I can do this better or something like that. Again, if you've seen me test out R1, you'll see me noting that. You'll see it in the thinking process. It'll be going along and it'll say, wait, oh, hold on, that's wrong. Or I could maybe do this better or something. It talks to itself like a person would talk to itself, which is really, really wild. So of course, this is a pure play in reinforcement learning. So what's the difference between 0 and R1? Well, 0 struggles with challenges like poor readability. Again, I think that this is a feature, not a bug. In other words, it mixes language. It's coming up with its own reasoning language. And it's also not as broad. It can't handle the more diverse things like things that don't have deterministic answers. And it's not necessarily aligned with human thinking. So that's where they create a pipeline to be able to create R1 that creates a reinforcement learning with human-friendly cold start data and some other stuff at the end. So number one, they want to further improve convergence and accelerate it by incorporating a small amount of high quality cold start data. In other words, train it on that data before you start the reinforcement learning. Also train user-friendly model that produces clear and coherent chains of thoughts and demonstrates strong general reasoning capabilities. In other words, beyond just deterministic stuff. In order to do that, they create this pipeline, which is a little bit complex to implement. It's fairly easy to understand, but like, wow, that's a lot of steps they have to go through. So the first thing they do is they collect thousands of cold start data to fine tune the DeepSeek V3 base as the starting point for reinforcement learning. So they grab that information, and I think they use V3 to actually create a bunch of this data. But anyway, they curate a really good list of data that they can use, high quality data that they can sort of jumpstart this thing with. So first thing, fine-tune DeepSeek V3 base on the cold start data, and then you apply the same large-scale reinforcement learning training process. So do the cold start training on this V3 model rather than starting from scratch, and then move it straight into the process that they used for the entirety of R10. That's the bulk of the training, let it go, but give it a head start. So now, instead of being a freshman in college and being there the first day of class or something, it's like a sophomore. It's already had a couple of years of education to figure itself out, and now you give it the problems and say, go for it, figure it out on your own. And of course, they talk about well-defined problems with clear solutions. This is a bugaboo for LLMs, as they said in my note there. It's a problem. The more distant you get from benchmarkable stuff, the more complicated it gets for it to solve these problems, which is why ARC is not really the biggest challenge and not what I would consider AGI worthy. The ARC challenge is, for whatever it's worth, I mean, it's a very challenging puzzle for AI, but it's a puzzle with a right answer. It's deterministic, makes it very easy, or straightforward, not easy, makes it straightforward for these things to be able to figure out how to solve them. The real world is full of things where there are not clear answers, and that we're going to get to at the end, but they clearly just kind of sprinkle that in as a little bit of spice on the end of this thing rather than it being the meat of it all. Anyway, after they do that bulk of reinforcement learning, they then do rejection sampling and supervised fine-tuning. When reasoning-oriented reinforcement learning converges, that's a mouthful, we utilize the resulting checkpoint, in other words, where they are right now, to collect supervised fine-tuning data for the subsequent round. So they collect the data from there. Unlike the initial cold start data, which primarily focuses on reasoning, this stage incorporates data from other domains to enhance the model's capabilities in writing, role-playing, general purpose tasks. So they're moving away from deterministic questions to more generalized questions to allow this to become a better model and answer more nuanced questions that somebody might ask. So this is step 3 in the pipeline. So anyway, they curate reasoning prompts and generate reasoning trajectories, and they get 600,000 reasoning-related training samples. And then they also collect 200,000 training samples for non-reasoning data. So again, it's pretty biased towards reasoning at this point, but they do throw in some of this stuff. Anyway, for non-reasoning data such as writing, factual QA, self-cognition, and translation, we adopt the DeepSeek V3 pipeline and reuse portions of the supervised fine-tuning data set of DeepSeek V3. So they're basically bootstrapping using what they already developed with DeepSeek V3. Really interestingly enough here, and I think this is a major advantage of R1 over OpenAI's O1, I've seen this happen many times, is that they actually train it for simpler queries such as hello or, simple stuff. We do not provide a chain of thought in the response. In other words, it's trained to be able to answer a simple question simply and not do complex thinking. I saw that in my testing with R1. With O1, when you ask it a very, very simple question, it will think about it for 60 seconds and generate a ton of tokens. That's stupid. It doesn't need to do that. Whereas with R1, if you ask it a simple question, it doesn't think very long and it answers relatively quickly. memory. So it's a more efficient model. It knows when to create a bunch of tokens and think about it and when not to bother with that. And then the final step is a reinforcement learning to kind of align it with human, human preferences, I guess. They implement a secondary reinforcement learning stage aimed at improving the model's helpfulness and harmlessness while simultaneously refining its reasoning capabilities. And down here, you can see that for helpfulness, we focus exclusively on the final summary, in other words, what it says, rather than what it thinks, so that they don't impact its thinking capabilities. So this is actually huge. You don't want to mess with its thoughts. You only really care about the outcome, not the thinking. You want to allow it to think as broadly as possible so that you get the best answer. But interestingly enough, for harmlessness, in other words, is it scheming or something? They actually do look at the reasoning process and they grade it on that as well. So, you don't want to restrict its ability to think as broadly as possible to create a helpful answer, but also you don't want it thinking about manufacturing illegal, weapons or biological agents or something like that while it's thinking. So the harmlessness aspect, you do need to kind of look at what it's thinking. So I think that this is a very effective way of training it and not getting your fingers too much into it, but allow it to be helpful and harmless and still provide the best answers possible. And then of course they talk about distillation of small models and how that really, really works, and how reinforcement learning just for these smaller models doesn't really work because it's just too complicated for them. Again, it's like a toddler. They can't handle this. Or maybe actually what we're looking at here is a chimpanzee or something like that, right? So you've got a model that's just not smart enough. Doesn't matter how much reinforcement learning, how much playtime you give it, the brain is not really smart enough to learn this thing. So instead, what you do is you distill out a lot of the knowledge of the bigger model into the smaller model, and you basically make the brain more efficient. You teach it how to do that directly instead of allowing it to try to learn because it's just not smart enough to do that on its own. So I'm going to skip over the experiment section. Again, you can read it if you want to, but we're already at a hugely long time for this video. But anyway, we get to the discussion, and first we start with this distillation thing. But you can see in this table, you've got the Quen 32 billion parameter just base model, and you can see the AMI scores, the Math 500, etc. You can see that on top. Then you've got the R1 basically reinforcement learning, trying to do basic reinforcement learning and have it learn on its own. And it actually does worse in some cases, or just barely better. But if you distill the knowledge down, then it just blows away its own model, right? It's still a 32 billion parameter model. It's the same model. It's just the weights have been retuned, and yet it performs so much better with the distillation of the knowledge of the bigger model. So that's really, really cool result. It's going to mean we're going to have a lot of very smart, very compact agents that are going to be able to do incredible things really soon, because this is all, again, open source, so you can use it today to train these things. They also talk about why process reward modeling, in other words, getting into the weeds and grading it step by step, doesn't work. Why Monte Carlo tree search doesn't work. It's kind of a shame. I kind of like Monte Carlo tree search, but it's very intense. It takes a lot of compute power. They said actually during inference it can actually be useful, but not very useful for training. So interesting and good to know. And then finally, they get to some limitations. So currently, in tasks such as function calling, in other words, it has to use tools, things like that, multi-turn conversations, complex role-playing, and JSON output, it's not as good as their V3 model currently. Or as my note over here says, it's smarter, but it's less constrained. It's not able to fit inside the box yet. So they're going to work on that, as they said. We also get language mixing, which again, I think is kind of a feature, not a bug. I think that's really fascinating. If I were them, I would do a branch of this experimentation and just allow it to go. See what happens. See if it develops this weird sort of, what would it be? Changlish or something? I don't know what it would be called. But if it develops this weird sort of mixed language and then actually starts to develop it even further to a point where it's able to create its own reasoning language that's not constrained by any of our human languages. I personally would love to do research in that. I think that would be absolutely fascinating. So I hope they do. I hope they take a branch of this and just go like, well, hell, let's just see what happens if we allow it to keep training like this, if it will develop its own reasoning thing. And if it does, can we take that and utilize that to teach other models that are more human friendly from this new reasoning language? Can we do that? That would also be amazing. Another really interesting thing here is that it's very sensitive to prompts. That seems a little surprising to me, and that few-shot prompting actually degrades its performance. In other words, giving it examples of like, hey, this is the question, this is the answer, that kind of thing actually degrades rather than improves the performance. So yeah, basically zero-shot setting is the optimal results for this. So that's actually good to know how to use this, and the fact that, if the prompt doesn't work and you don't get the right answer, try tweaking the prompt because it sounds like it's very sensitive to that. And then software engineering, in other words, big tasks. They haven't really given it a lot. It sounds like they're just resource constrained. They don't have the time, they don't have the compute power to give it these ultra long duration things. Like, it's not like write me a program, it's like write me this entire, software suite or something. That is a little bit beyond its capabilities at this point, so it's unable to perform well. And then of course I would also throw in here, I don't know particularly how good it is in terms of doing more creative tasks that don't have as many deterministic outputs. In other words, creative writing or thinking philosophically or things like that don't have deterministic outputs. Unclear how good it is with that. But even given all of these, these caveats here, this is an absolutely amazing milestone in the race towards artificial general intelligence. Like I said at the beginning, this blows the doors off of any kind of constraints that are based on humans, because we can just turn this thing loose and let it play. Now that there's a methodology for how to do this, we can just turn this thing loose, allow it to play on its own data. And I don't know, we could be within 6 months or a year. It could be as little as that. We could be looking at something that is smarter than any human being on the planet, and that would be both terrifying and awe-inspiring. All right, so that was an absolutely huge video, a lot of details. I hope it was worthwhile, and I hope I helped you to understand why this is such a big deal. If I did, please give the video a like, and if you don't mind subscribing for my birthday, that would be great, and I will see you in the next video. Bye-bye.